Hello, my name is Laura Carbone and I work for the Department of Engineering at Huesker Synthetic. Today I will briefly address the issue concerning a landfill cover system, discussing the major aspects regarding these types of design using geosynthetics. A controlled landfill is a site specifically designed and developed for waste disposal. The landfill is, for all intents and purposes, a reactor in which liquid, solid and gaseous materials react, causing liquid emissions, leachate, gaseous emissions, biogas, within a solid matrix, that is, the waste in place, that represents the source of the potential residual emissions. Emission control is typically carried out through the use of a multi-barrier system that prevents the uncontrolled spread of the emissions into the environment. The barrier system of a landfill consists of three main elements: the base barrier, the lateral barriers, the top cover. Let us now examine the cover system. The final cover of a landfill must perform the following functions: isolate the waste from the external environment, minimize surface water infiltration, minimize maintenance costs, minimize the surface erosion, tolerate only differential settlements and the possible phenomena of localized subsidence. The layers can be alternately constituted of mineral materials, namely different types of soil, or of soil geosynthetic composite systems, once their functional equivalence with mineral layers is demonstrated. Nowadays, the use of geosynthetics in such systems is widespread, and it offers considerable advantages compared to traditional solutions. Geosynthetics are materials that are quick and easy to install. Their use allows us to greatly reduce emissions of carbon dioxide in the environment. In fact, for example, considering solely the transport within the construction site, 150 trucks of clay having the capacity of about 20 meters cubed each are equivalent to a single lorry with trailer containing a bentonite geocomposite. Moreover, thanks to their thinness, geosynthetics allow the increase of the volume capacity of the landfill. This volume can be further increased through the use of a particular class of geosynthetics, namely those which function as a reinforcement. These materials have a high tensile strength and enable the construction of side slopes with steep inclinations. In designing a composite cover consisting of layers of geosynthetics and soil, there are three main failure mechanisms which are consequently associated with three stability tests: the global stability of the slope, the internal stability of the cover soil layer, the stability of the whole system with particular reference to the interface between the component parts. Let us therefore examine the failure mechanism with reference to the interface system. Let us imagine we have a system composed of alternating geosynthetics and soil. Generally, the stability analysis is carried out by means of limit equilibrium analysis while examining the interaction between the different interfaces of the system. In this analysis, the layer of soil, considered stable, exerts a load on the underlying system determined by its own weight. The destabilizing force generated under static conditions is opposed, assuming an indefinite slope, only by the resisting force exerted by the critical interface which has the lowest value of the angle of friction. We assume, therefore, that the resisting force is purely frictional, and consequently the critical interface represents the possible failure surface. Stability is achieved when the resisting forces are greater than the destabilizing forces. If stability is not achieved, it is possible to use a geosynthetic providing a reinforcement function, such as a geogrid, which can bring to the system the tensile strength required to satisfy its stability. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which must be designed according to the load. This tensile force will be transmitted to the anchoring trench, which m Anchor trenches may therefore have different geometries depending on the acting force and the different site constraints. I hope that this presentation has been of interest to you. For any technical details or further information regarding Huesker Synthetic Solutions, please visit our website or contact us personally. Thank you for your kind attention.
E alla prossima.